You're welcome. In this video, I'll be walking you through the concept of hybridization. And under hybridization, we need to understand the concepts or the fundamentals that builds up the concept of hybridization. And one of these fundamentals will relate us to atomic orbitals. So let's start with what is hybridization. Hybridization is defined as the mixing of atomic orbitals that are within the same principal quantum number. The mixing of atomic orbitals that are within the same principal quantum number to form new orbitals. Now, these new orbitals that are formed are known as hybrid orbitals. The new orbitals formed are known as what? Hybrid orbitals. More like an hybrid coming from a parent. So the atomic orbitals can also be referred to as the parent orbitals. And under chemistry, we have three different types of hybridization, of which the first one is Sp3 hybridization. The second one is Sp2 hybridization. And the third one is Sp hybridization. I would like to take us back on the previous or fundamental knowledge for this concept, which are the two common atomic orbitals that we will be working with, S orbital and the P orbitals. From our basis of chemistry, we understand that there are four different atomic orbitals known, and those are what? The S orbital, the P orbital, the D orbital, and the F orbitals. Now, the S orbital is known to be the one with the lowest energy level, followed by the P orbitals and the D orbitals in order of increasing energy level. So, under the concept of hybridization, we can have Sp2D hybridization. We can even have some hybridizations that involve the D orbitals. But majorly, we have three main types, which are the Sp hybridization, the Sp2, and the Sp3 hybridization. Like I said earlier, it's basically taking us through the S orbital and the P orbital. The concept of hybridization is a very important concept in the field of organic chemistry because it is like the basis or the foundation of organic compounds. Knowing fully well that carbon exhibits tetravalency, which is one of its characteristic property and unique property for it to catenate. For this reason, we will be starting with Sp3 hybridization. We'll be starting with Sp3 hybridization. Like I said earlier, we are relating it to the field of organic chemistry, which is the basis for organic compounds. And organic compounds are compounds of carbon with other elements like oxygen, hydrogen, nitrogen, sulfur, chlorine, and so on and so forth. So, if carbon is the main element and the major element in organic chemistry, there must be a unique property of carbon that allows or gives rise to hybridization. And we will be starting from the electronic configuration of carbon atom. Carbon, as we know, has the atomic number of 6. If carbon has the atomic number of 6, the electronic configuration is given as 1s2, 2s2, 2p2. But this can further be explained and broken down to 1s2, 2s2, 2px1, 2py1, and 2pz0. Now, what have I done? I have exhibited the property of the magnetic quantum number, which relates atomic orbitals to their orientation and degeneracies at which they can allow. So, p orbitals has three different orientations or degeneracies, which are known to be px, py, and pz. Now, these degeneracies are known to have equal or relative energy. And if the electronic configuration of carbon is written, we have 1s2, 2s2, 2px1, 2py1, 2pz0. And this is not just written, it is following a particular rule in chemistry, which is known as what? It's known as the Un's rule. Un's rule. Un's rule of maximum multiplicity is a particular rule that electrons use to fill in degenerate orbitals. And what does Un's rule say? Un's rule states that electrons fill in degenerate orbitals singly first before pairing. And that is why when filling in the atomic orbital for carbon, we do not have this, but rather we try to go singly. After filling X, we go to Y. If it happens to be that we have another electron, we put it on Z before coming back to pair them up, starting from X. So following Un's rule of maximum multiplicity, we fill in our ground state electronic configuration of carbon to be 1s2, 2s2, 2px1, 2py1, then 2pz0 happens not to have any electron. Now this is the ground state electronic configuration. Now, the ground state electronic configuration is given as this. From Niels Bohr's theory on the structure of an atom, one of the postulates of Niels Bohr made us understand, and even Albert Einstein also worked on it, relating it to light, which is photon. And under Niels Bohr theory, Niels Bohr made us understand that it is possible for an electron to gain energy. And when it gains energy, it moves from the ground state to an excited state. In other words, it means when electrons are in constant motion and energy happens to be supplied to them, they happen to move from the ground state to an excited state, meaning the electrons can move from one orbital to another orbital. What is the definition of an orbital? An orbital is called the region in space where the possibility of finding an electron is maximum. Again, an orbital is the region in space where the possibility of finding an electron is maximum. Now, if it is possible for an electron to gain energy to move to an excited state, electrons also gain energy when they are ready for bonding, and that is one of the process or reason for hybridization, to set the electrons or the atom for bonding. So when the electrons are actually ready to be bonded or to create a bond, they receive the energy to proceed or to jump into an excited state, which will give us another configuration of carbon when it is excited. Now, carbon in an excited state has an electronic configuration of 1s2, 2s1, 2px1, 2py1, and 2pz1. One, two, one, 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 one. What has happened in this place? It means that the 2s orbital has released a particular electron to be excited to go to the 2pz orbital. The reason for this, from the definition. We said hybridization is the mixing of atomic orbitals within the same principal quantum number. And one of the usefulness of the principal quantum number is that it gives us the energy. So we are likely saying within the same relative energy. They happen to be in similar energies. So it is possible for 2s electron to be excited and release one electron to move into the 2pz. Now we have 2, 1, 1, 1, 1. And from what we know, atoms strive to gain octet states. So these lone pairs of electrons are actually ready to be bonded at this excited state of carbon. Now, at this excited state of carbon, carbon is ready. Carbon is available. Carbon is ready for bonding. And if carbon is ready for bonding, it happens to be on the lookout for which is available that could bond it. And that's why we will be giving a particular common example of Sp3 hybridization. And the example of Sp3 hybridization we'll be working with is methane. Methane as an example of Sp3 hybridization. This formula for methane is CH4. CH4, where we have one carbon atom and 4 hydrogen atoms. At this excited state of carbon, carbon is ready and available for bonding. So, hydrogen, which is also striving to be stable, having the electronic configuration of 1s1, trying to gain duplet state so it can be stable or attain the structure of helium. Like I said again, hydrogen has the electronic configuration of 1s1, trying to get the duplet structure or to attain the electronic configuration of helium, which is 1s2. So it can be stable. And for this reason, hydrogen is on the lookout for an available bond pair, an atom or an electron that is available for bonding. And because of this reason, when hydrogen approaches carbon for bonding in the structure of methane, the hydrogen realizes, or let me say, since we have 4 available lone pair of electrons waiting to be bonded or to get paired with an electron, and hydrogen having 1s1, just one electron, is able to attach itself with every one of them, having its 4 hydrogens to the structure of this carbon. So we can have, let's assume we are representing the electron of hydrogen to be in circles. So we have, or probably let's still use the arrow diagram. Now, if hydrogen comes here for bonding, another hydrogen attaches here for bonding, another hydrogen attaches here for bonding, another hydrogen attaches here for bonding. So we have had a total of what? 4 hydrogen atoms attaching itself to just one carbon atom. And this is how the structure of methane is formed. The net electronic configuration that we'll be having, will now be 1s2, 2s2, 2px2, 2py2, and 2pz2, which has given it the stability the compound desires. So this concept is known as Sp3 hybridization. Why? Because we have one s orbital hybridizing with 3 p orbitals. The s orbital is the hydrogen atom hybridizing with 3 p orbitals. It could be known that s orbital of the hydrogen was on this s orbital, and the bond that was formed was an s to s bond. But when it attaches to p, it became s to p, s to p, and s to p, having a total of what? Sp3 hybridization. In other words, it can also be said that we have one of the two s orbitals hybridizing with three of the two p orbitals, and that is why we have Sp3 hybridization. Now, the structure or the bond angle, because every hybridization causes an alignment, so it is known that the s and the p orbitals align at almost right angles to each other. So the shape of Sp3 hybridization is tetrahedral. So Sp3 hybridization is known to have a tetrahedral shape. And the diagram of the methane structure, is in the tetrahedral form, where we have the carbon atom and the hydrogen atom. Now, this is the structure of the Sp3 hybridization with a bond angle of 109 degrees. So this is a popular example of Sp3 hybridization. And on this note, we will be moving to the concept, or the second concept, of Sp2 hybridization. Sp2 hybridization. This is not so different from the earlier discussed hybridization, knowing fully well that our ground state, carbon has to move to an excited state for bonding to take place. So from the ground state, we have the carbon atom to be 1s2, 2s2, 2px1, 2py1. It needs to be excited so bonding can happen. So at the excited state, carbon becomes 1s2, 2s1, 2px1, 2py1, and 2pz1. Here we have 2pz0. So 2py1, meaning the 2s orbital has released one electron to the 2pz orbital available for bonding. But now, because it is Sp2 hybridization, likewise like the earlier discussed one, or the aforementioned type of hybridization, hydrogen could approach carbon having one electron, because why? All it needs is just one of it to attach to one particular orbital, and it gains its octet or paired state. That is why an example of Sp2 hybridization is the ethene. And the structure or the formula for ethene is C2H4. Now, what is Sp2 hybridization? Sp2 hybridization is the process of or mixing of atomic orbitals between the 2s orbital and two of the 2p orbitals. Again, one of the between the 2s orbital and two of the 2p orbitals, thereby leaving the 2pz unhybridized. Leaving the 2pz unhybridized. So if the 2pz is left unhybridized, that means that only two of the 2p orbitals is available for bonding, or is used for bonding. And just like we have in the ethane, having 4 hydrogens or 2 hydrogen atoms coming in place. Now, first and foremost, if an hydrogen atom should approach the excited state, we have an hydrogen atom here, we have an hydrogen atom here, we have an hydrogen atom here, thereby leaving the 2pz unhybridized. Now, because of this, we have one s and 2 of the p orbitals, and this is what has led to sp2 hybridization. But something is wrong. Are we going to leave the 2pz orbital unhybridized like that? No. That is why something must happen. Because of this reason, carbon picks itself with or pairs itself with another unhybridized carbon. With another unhybridized carbon. And under this concept, when carbon mixes with another unhybridized carbon, that is why we have 2 carbon atoms for this structure. Now, if another excited state carbon that is unhybridized pz, 2pz, comes in contact with this to form a bond, the pz of the new carbon and the pz of this carbon can pair together, thereby forming a pi bond. Thereby forming a pi bond. Now, this is responsible for the double bond structure we have in the structure of ethane. That is why when we draw the structure of ethane, we have something like this. Meaning it has one sigma bond from the hydrogen and carbon atom, then the pi bond of the p to p orbitals that are unhybridized of both carbons. Now, it is said that in ethene we have what? The sigma bond, and we also have the pi bond. Now, this is the theory behind sp2 hybridization, and the shape is very, very important because it is popularly asked, or if to test your knowledge on hybridization, you would be asked or told to describe, to define, to also give the shape as well as the bond angle. And a popular example, I've given an example which is ethene, and the shape of sp2 hybridization is trigonal planar. Trigonal planar shape with a bond angle of 120 degrees. 120 degrees. So the structure of sp2 hybridization can be drawn in this manner, 120 degrees. So this is all on sp2 hybridization, and we will be going to the third form of hybridization, which is sp hybridization. Sp hybridization. Now, under sp hybridization, we still have our excited state carbon when it has moved from the ground state to the excited state. When it has moved, now, like I was saying, the excited state of carbon is where we'll be working with, having known the ground state electronic configuration of carbon. And carbon in its excited state has, like we aforementioned, 1s2, 2s2, 2px1, 2s1 rather, 2py1, and 2pz1. Now, carbon is at its excited state and is ready for bonding. Now, if carbon is at its excited state, let's draw the structures of carbon in its excited state. Carbon is ready for bonding. And if carbon is ready for bonding, like before mentioned, hydrogen atom, a popularly lonely electron trying to attain duplex structure. An example of Sp hybridization that we'll be using to understand this structure is the ethane, which is this formula for ethane is C2H2. C2H2. Now, if carbon is at a excited state, it means just two hydrogen atoms are coming in contact with the hybridization, with the excited state carbon. And these two hydrogen atoms can rest here and can also rest here. So, what can we deduce from this, from the definition or what we have seen so far? It means that Sp hybridization is the mixing of one of the two s orbital with only one of the 2p orbital, which is the 2px. Now we leaving 2py and 2pz unhybridized. 2pz unhybridized. That means just like we had in the sp2 where we had just 2pz unhybridized, now we are having y and z unhybridized. So for this purpose, a carbon bond will be formed between another carbon which is unhybridized, just like we have two carbon atoms. So another carbon that is in its excited state will come in contact with this and form a pi bond at the 2py that is unhybridized and the second 2py that is unhybridized, so that stability can take place. And this is why the structure of ethane, you have triple bond in the structure of ethane. And this triple bond, we have one sigma bond and two pi bond. 2 pi bonds. That's plural. So, we have one sigma bond and 2 pi bonds in the structure of ethane, due to the fact that what the 2p orbitals that are unhybridized pair with another p orbitals from another excited state carbon, which is the second carbon atom, to form the pi bonds. Because we know when we have p to p overlap, this leads to the pi bond, especially our py and pz. We have our pi bonds. So the structure of Sp hybridization is known to have a linear structure. A linear structure with a bond angle of 180 degrees. 180 degrees. And a popular example of Sp hybridization is the ethane, which is C2H2. Now, this is all on the concept of hybridization, except that before we round up, hybridization influences the bond length and the bond strength of a compound. Hybridization influences the bond length and the bond strength of a compound depending on the S character. So for Sp3 hybridization, the S character here is 25%. The S character for Sp2 hybridization is 33%. And for Sp, the S character of hybridization is 50%. Now, what is the significance of this S character? This S character signifies the closeness of the s orbital to the nucleus of the compound, forming these structures. Now, these particular characters has an influence to play on the bond length and the bond strength. But let me tell you that the bond strength and the bond length are related by inverse proportionality. So, meaning the bond length is inversely proportional to the bond strength. And I will be letting us know that Sp3 hybridization with respect to bond length has the highest bond length to Sp2, then Sp hybridization. So the one with the greatest bond length is what? Sp3 hybridization. Because why? It contains just a sigma bond. But the more the number of pi bonds, the shorter the bond length. And that is why when we talk about the bond strength, like I said earlier, we have inverse proportionality. So Sp3 is going to be less, or let's say Sp is going to be the one with the greatest bond strength before you have Sp2, before you have Sp3. So the one with the highest or largest bond strength is Sp. Now, let's just take a particular question to relate whatever we have learned so far. If a question states that with respect to the S character, arrange these compounds in order of their bond strength. We have CH4, we have C2H4, and we also have C2H2. Arranging these compounds in the order of their bond strength. We said the one with the highest bond strength is ethyne or Sp hybridization. So first you need to understand the hybridization of each of them. This is Sp3, this is Sp2, and this is Sp hybridization. So the one with the largest bond strength is Sp, which is what? The ethyne, C2H2, followed by C2H4. Then lastly, the weakest one among them, which is what? CH4, in order of what? Their bond strength. If the same question is asked in another way around, relating it to the bond length, like I said earlier, bond length shows inverse proportionality with the bond strength. And at this juncture, that is the end of hybridization in chemistry. Talking about Sp hybridization, Sp2 and Sp3 hybridization. Let's not forget the bond length, the structure of the compound, a particular example, as well as how to draw the structure. Please subscribe to our YouTube channel, Further Solution Academy. I hope you enjoyed this video. Thank you.